Good morning. A little bit later than I expected, but we have one person in the classroom right now, so those of you that decide to backfill by watching it, the video, that'll be your option for sure. I did finish the grading last night. I posted the histograms, updating what the grading had consisted of, and creating some preliminary histograms of what I call the pre-average, and I'll walk through that. That is on the website right now. I pushed the exams back to you on Slack earlier this morning. I've seen that those arrived, and I also pushed up the solutions to the exam. However, all my annotations made my stupid PDF take 20 megs without compressing it, so I have to fit in that 8 meg ceiling that the WordPress website has me on. So I put the solutions into Slack on the Modern DSP channel, so you can look at them there, and that's how I have them downloaded. I don't even have a lock on it, so you can just open it right up. And I am going to talk about the exam, but I don't think I'll talk about it until more people are here. I also have pushed up project number 1. The Julia needs to be removed from that, but if you were to zoom in and look at the dates that I have on here, it is 2024, and I'm tentatively saying it'll be due Wednesday at 5 p.m., just before Thanksgiving. I have been known to extend that till the following Monday, because I know you're also going to be working on getting the take-home exam done by, generally it's been Tuesday. This year, in all my existence at UCCS, and up until this year, Thanksgiving week has always been a week of classes from Monday and Tuesday. So I always figured if I gave a take-home exam, I could have it due on Tuesday, regardless of whether we met or not. And as a matter of fact, we wouldn't have met, because in the old way of doing business, Monday and Tuesday were class days, Wednesday, Thursday, Friday or not. But that would line up with Labor Day. If you remember back, Monday and Tuesday, or at least Monday is off for Labor Day, and then, I don't know, I always looked at it as a complete week was taken away with holidays and things. But at any rate, this year they're giving you the whole week off, but I don't want to sacrifice having you continue to work on things. You're paying good money, and I want you to get your money's worth. So that take-home exam will be coming, the week before Thanksgiving, in about 3 weeks from now. So if we were to look, I guess I should look on the calendar since I've got it here. It'll be coming on like the 21st of November, and it'll be due, say, nominally on the 26th. I'll just say 5 p.m. on the 27th. In Slack, and the project is also due then as well, and I'll be spending a lot of time talking about the project problems. I'm going to start on that today, as a matter of fact, and there's actually hints for the project 1, problems 1 and 2 already in the hints, or already in the notebook for chapter 4, so you can see those, and we'll probably look at those if we have time too. So that's kind of that layout for now, and I'll come back over to this eventually. Let me just get this staged since it's already here. Pull up this histogram page if I can. And we'll be talking about that later. Our class is so teeny tiny right now that a histogram is almost pointless, but I have this in Julia that I put together 2 years ago, so those are the exam scores. I do want to, like I said, I do want to walk through some of it, but I'll just say my preliminary comments from the histogram. The average is definitely not the distribution is shifted low by at least 10 points, maybe even 15 points, by my recollection of what I would have been hoping for. Don't have an explanation for that, except maybe it's You know, I could be at fault. The fact that I'm retired from teaching officially and coming back, maybe I shouldn't be doing this anymore because it's not working. I don't know. I can blame myself. You can blame yourselves for dumb mistakes. I don't really care so much about that anymore because time doesn't go backwards, it goes forward. So we're going to go forward and we're going to make it work. And I did do a composite histogram here too, where I weighted, I guess I'm into this, I'll talk about it, I just want to talk about the exam. So what I did was to get an idea of where we're headed. This is just how the math works out in Julia. I took the average of the histogram distribution at 0.25, because that's what it's going to count at the end of the semester, 25%. And my super sensitive mouse won't let me touch it without jumping the page around. And then I took exams 1 and 2, which 2 doesn't exist, it's just filled with zeros right now, and weighted that at 15%. And I weighted the project at 20, which would be project 1 and 2, since it'll be a final project, sort of an applications project. And then I took the final exam and weighted it at 25%, and that doesn't exist right now. Actually, in the end of the semester, the project and the final exam are in a teeter-totter kind of relationship where I adjust automatically, if you remember from the first day of class. The final would nominally count 30%, and the projects would count 15%, or whatever the number is. I think I coded that in right. But at any rate, I'll fix that if it's not coded in right, and then it will be optimized in my spreadsheet. For right now, all that matters is I've only got 2 numbers into this pre-final average, a weighting of 0.25 on the homework, which is very far from being complete, but it sets 1 through 3, and then I'm weighting the single exam at 15%. But then in order to make it come out to 100, I take that compositing, or that weighting, and divide by those 2 numbers. So again, I'm on a basis of 100. And when I do that, the fact that people have done well on the homework is kind of mitigated now in this histogram. You can see that the numbers are looking better, more to what I would be expecting. So that just shows you why there's 2 exams and why the exams are only 15%. And so don't beat yourself up about it. You can have a bad day and other things can happen, but we'll come out of this okay. I don't really have a serious problem. If you stop working and become disinterested, you know, then it's not a good thing. But stay motivated and stay enthusiastic about doing DSP. I'm maybe too enthusiastic because I'm doing it every single moment that I work at this company, which is only half-time, but I'm just really excited about things, and that's one of the changes I made in the project. Problem number 3, rather than it being a polyphase filter, I've decided to make it into a numerically controlled oscillator investigation that's based on an accumulator of 48 bits, and it's based on an accumulator that's 48 bits wide because there's something called the DSP slice in AMD/Xilinx FPGAs, and that is being used on the project I'm working on right now for a phase accumulator and for event structuring in hardware description language code. So I'm trying to make this a miniature little look at the types of things that I know people do in practice when they're putting their systems up in FPGA. So, and I've been having fun with it. I just didn't start doing that since working for the current company. I did it for a consulting project over a year ago on something that involved kind of trying to model in Python or Julia things that would happen in FPGA code. So the scores is something else we have to look at, and that's down here, but I'll wait and see what materializes later today in terms of who's going to be here. So instead, I'm going to go back into where we were and kind of try to get back into things, and then proceed through some examples, and then hopefully more people will be here. So I just talked about the exam histograms, but I haven't talked about the problems.
Is the histogram on your website?
Yeah, it's on there. We were just looking at it. Yeah, you'll find it where I've kept it all along. When you're here and you type histograms, I updated it last night, and we were just looking at it. So we actually already went through it. But you can talk to me at break time or something, too. Everybody that's either currently in the classroom, we now have half the class here, which is a big wahoo. We're halfway there. You've got my grading, and the solutions are also in Slack, because they were too big to post on the website without some massaging and compressing. So I want to get back into this, and then this will motivate our needs to maybe discuss the project problems too, and of course the homework that's due. Really what's due in the homework, I've pretty much covered everything when we covered upsampling and downsampling. There's a bonus problem that involves some numerical integration, and I give hints on that, but that is a bonus problem. It's workable, it's definitely workable, but I don't want you to bend over backwards and worry about it. But I do have pretty good hints on it in there, and those are up there. We can look at them too. So we talked about upsampling or downsampling, and then upsampling and using low-pass filters to keep things in order. The pre-filter to the downsampler is for aliasing protection, and the post-filter in upsampling is for interpolation, to fill values in. I mean, two very crude things that if there's not a filter thrown in there, you can run into problems. I don't know what is worse, but I actually think the upsampling is worse, because the upsampling is, aliasing might be manageable to some extent when you downsample, but if you upsample and stuff zeros in, L-1 zeros, it's like this waveform is very raw looking. It doesn't have these spectral images taken out of it. So, and that's what, I'm alluding to what we talked about last week, where you get these extra spectral images in there. Like this is a spectral image, and then when we come along with our interpolation filter, it's a low-pass filter with cutoff pi over L, and it gets rid of that spectral image. So when I was nearly passing out last week, it's not as vivid for you probably as it is for me, but I was trying to look at this, and it kept getting darker and darker, and I was like, wow, I'm feeling really bad. That was the worst I felt ever, I think, in a lecture, and I don't know what it was. It passed through my system, whatever it was. But this is an exciting example that I was trying to walk through, explaining how in compact disc digital audio, this was back in the 70s, the people that implement A to D converter, or digital to analog converters, which is needed in the playback of digital audio, initially knew that they needed 44.1 kilohertz sampling rates and at 16 bits per sample of stereo audio, because that was what Philips and Sony came up with. Have I talked much about the history of the compact disc? It's pretty interesting. Sony and Philips are two electronics and other things. Philips makes appliances. You might have a Philips Sonicare toothbrush. They're all over the map in what they make. And Sony makes a lot of electronic stuff. But they came together and established the format for the compact disc. They said it would be 44.1 kilosamples per second for audio that was, mastered in a studio or live, and then maybe it was done at 48 kilosamples per second back then. But supposedly the story goes, and there's a digital audio book that I think I still have. I may have actually not saved it when I moved out of my office here, but said that Beethoven's Fifth Symphony, which is pretty famous, everybody's heard it before, I'm sure. It's used in a lot of places. that one of the two of those presidents, or maybe it was both of them, said, we want Beethoven's Fifth Symphony, when recorded on a compact disc, can fit in its entirety at the typical tempo a conductor would take it at. So they wanted to have enough capacity on the disc to have the entire symphony there, and that was supposedly how they kind of backed into some of the parameters that created the first compact disc. Is that believable? I mean, I think you have to be driven by a desire for something in a device. You just can't say, let's make this device. What are the constraints? I mean, that's the life as an engineer. It's not just build what you want to build, it's build something that meets some requirements. So that's what they came up with. So I don't know if that's exactly why 44.1 was arrived at. It might have something to do with the availability of technology and other such things. There's coding and put into a compact disc as well to protect the bits so they can be played back error-free. So it's not just simply multiplying some numbers together based on the sampling rate, 16 bits per sample, stereo, and coming up with how many bits per second have to be for so many minutes on the compact disc, because there's forward error correction using a Reed-Solomon code, and then there's framing and other things to put it all together. But that's how this was established. And then when it comes to having those samples and looking at playing things back, you have to have a sharp cutoff filter in order to separate the images that are going to come in from the spectrum that's sitting up at 44.1. And of course, we know from our hearing that in reality, we only care about that being say about 16 kilohertz. I'm just, guessing. I think musical recordings, we'd like to have it higher than that, but if we could go up to even 20 kilohertz, that would be good. 16 kilohertz. They used to say in high-fidelity audio equipment, you wanted to be able to go from 20 hertz up to 20 kilohertz, even though most people can't hear, even when they're young and have greatest abilities, much above 16 kilohertz. Why do I say that as an example? You're mostly probably can't remember. We used to have analog TVs, and they had a sweep rate of 15.525 kilohertz, where it was doing this raster on the screen. And when the TV set was turned on, when I was younger, I don't notice it anymore, if a TV set was turned on, you would hear that 15 kilohertz really high-pitched whistle, and it was very annoying to hear that. So that proved to me, when somebody in my family, probably my father, said, you're hearing the TV, it's bothering you, right? Eventually you don't hear it that high in pitches, and I guess another disappointing thing is Bluetooth Classic, which is what these earbuds are using, and most earbuds today use, cuts off at around 12 kilohertz. I don't know, have you ever noticed that Bluetooth audio doesn't sound quite as crisp as direct from your CD? So you've noticed that, have you ever? What, is that aggravating or not? As a high fidelity, music listening type person, I always thought, why did we do that? Well, the technology, again, forced Bluetooth to be reasonable for audio, and they said, we'll make a compromise. We'll cut off the high end a little bit, and most of the population probably doesn't care, and most of the population probably wants heavy bass. They don't want any high frequencies. But, that's really subjective, right? That's not totally fair, but that's what they did. I think the new Bluetooth LE audio standard, which has a codec now in it to compress and decompress, I attended this workshop 2 weeks ago now, is probably going to improve that a little bit better, and it will have better battery life, is my understanding. So the new generation of earbuds that's going to come out, and I think Sony actually already has that out, no other vendors do, is going to do a lot better. Your phone needs to be upgraded now. The software, the operating system software of all the phones has to come into compliance, because the phone is going to act as the controller for what's in the BLE2 audio, which will be like in the earbuds here or something similar to that. There's a lot of cool features, though, that it's going to bring. I'm excited after attending the workshop because it's going to allow overlays of audio, not just one track. So you're listening to your music, you're in an airport terminal, and they've got a broadcasting system set up to say when flights are leaving or arriving and stuff. It can just overlay, depending upon how you configure your phone to talk to it. That's my understanding from the workshop I attended, which I think is pretty nice. A lot of features that they thought about to add to this new generation. But at any rate, back in the 70s, a big innovation was how can we not have to introduce frequency droop, which is what happens when you just go through a zero-order hold that's in the D to A converter. The zero-order hold is sort of a natural thing. When the converter finishes a cycle, it holds that value that it outputs. It's a flat top pulse, and then it gets updated again at the next clock cycle. So that introduces the sync function roll-off that I've got shown in here, and that impinges a little bit on our 20 hertz to 20 kilohertz passband that we're trying to get audio through. It also doesn't totally remove the spectral images that we see up here when you try to reconstruct the analog domain. Now, most cases you'd say, I don't care, I can't hear up there, but what the problem is if the audio chain can respond to these frequencies, and that just adds more energy into the overall spectrum, that you might get some intermodulation or other things happening, compressing going on in your audio signal processing chain. So you do want to remove those higher frequencies best, to some extent. Does that, from an electronic standpoint, does it make sense that the more information you send through a channel, you're just going to bring it to compression where it's distorting? And an intermodulation, when you have a nonlinearity present, can make something from a high frequency multiplied times another high frequency, and then it can create a difference down in band. And then for RF signal processing, that's pretty bad stuff that can happen with intermodulation products. And I'm not going to go into that right now myself, but so what did they come up with? They said, okay, we're going to upsample before we leave our D to A by a factor of 4. And what that is going to do, and we're going to use a digital interpolation filter to remove all the spectral images that would normally be here at 44.1, 88.2, and so on, and we'll just have the natural image, which is going to be at the 4x sampling rate, to deal with. But now that we've done that, our big constraint for back then was the audio converter has to run at a 4x sampling rate at 16 bits and in stereo. I think the analog engineers took that challenge on, and they produced that low-cost part, and the history was made. And then the only thing that remains is removing something way up here, but because of the natural roll-off of the sync function, it's going to be easy to get rid of that. So that was significant innovation, and you would see that on devices you would buy. It would say, on devices I bought, 4x oversampling, or later they started talking about how the sigma delta converters will do 64x oversampling, and that showed up, let's see, I think it's a Sony compact disc carousel player that I've had in my household for a long, long time, but it has something about the converter used and how it's so fantastic. I mean, the technology went beyond it, but this was an easy one to understand of why you might want to upsample before you leave the system. And in software-defined radio, that it's generally done that you will upsample to a higher rate in order to put some ability to adjust center frequencies and other things before you actually put it up on the RF carrier. So upsampling ideas are just commonplace these days. You have, in the RF world, you have the digital down converter to take it off the carrier put it into an oversampled DSP domain, and then you can down select from there. That's our next example, actually. And then at the opposite end, when you're transmitting, you have the digital up converter. So DDC, not that it's an acronym that's not used for something else, but digital down converter is that acronym, DDC, and then at the other end it's called the DUC. And I think I actually, I had some links that I put in to the websites of Analog Devices and AMD Xilinx. I may go look at those at some point here. So the next example of how you can take advantage of multi-rate sampling is in a digital radio receiver, and this is a pretty old technology at this point in time too. This example was written when 2G cellular telephony was in place, and we had code division multiple access going on, and this example is kind of built around that idea where it was a spread spectrum scheme, and that was Quest was the original service provider for the Front Range of Colorado, and then I'm trying to remember who did Quest turn into. Does anybody know? Because you probably can't even remember what Quest was. They were a telephone company. But at any rate, the two bands that are used for cellular to this day is the so-called cellular band around 850 megahertz, and then the PCS band around 1900 megahertz. PCS is an old acronym, but Personal Communication Systems. Make sense? And before we had digital cellular telephony, we had analog cellular telephony. So that was the 850 megahertz band, and it just got the fabulous name cellular band because it was like the very first thing that got allocated by the FCC for cell phones. So the standard thing to do in a receiver is to convert a signal right off the carrier by multiplying by a high frequency carrier and taking it down to baseband. So what that means is that it was at 850 megahertz, I would down convert it with an RF mixer, one operating with a cosine around 850 megahertz, and the other one with a sine, and that would implement an e to the minus j something or another. So a signal spectrum is up at 850. If I multiply in the analog domain by a real signal that's a cosine, a real signal that's a sine, then I can implement this complex frequency translation of shifting it down to around 0 hertz. We know that complex frequency translation exists in the analog domain. It's just you never really think about it because you say a signal generator that has two outputs for one input. I mean, that just seems to get a complex signal. That seems bizarre, but it's what would be done. And then you would have two A to D converters from each of those mixer outputs to get it to complex baseband, and then you would make sure it's filtered to the Nyquist rate, and then you would be able to get it into the DSP domain. A second, the one this example talks about, is so-called IF sampling, and it's still in use today, and we're going to get into that in a second. The third one I listed here is direct bandpass sampling, and that's what people have been talking about as the most forward-thinking approach to radios that want to do their signal processing in DSP, where you just directly sample at the RF, at the microwave carrier. You don't do any converting down to an intermediate frequency or anything. And that is making a lot of progress. There's direct sampling available in AMD Xilinx's RF SOCs, and there's different types of A to Ds that can manage that. Analog Devices has a bandpass sigma delta, which is like the generation beyond the standard audio sigma delta, where you can sample directly at RF, and then you have a shaping filter that's built into that. those things have been more expensive, but they're less expensive now. So, but in the interim, though, the IF sampling idea came into being. And so in the IF sampling, the received signal comes in, and your RF front end, a microwave front end, low noise preamp, maybe automatic gain control and other such things in there. And then a local oscillator would convert it with the modulation theorem down to an intermediate frequency. And in the beginning of all of this, people wanted to use about 70 megahertz as the intermediate frequency. That has since shifted up higher, but it was driven by technology. I mean, what isn't driven by technology? We want to do something, but how are we going to do it? What's the technology we have available? So all the parties involved say, I think we should use a surface acoustic wave filter. That's a technology where you actually put on a lithium niobate substrate, a pattern, a metal pattern, and rather than using transverse electromagnetic modes like in microstrip or other strip lines that you might use in an RF PCB, this material, lithium niobate, lends itself to an acoustical wave propagation over that substrate. Now this, have either of you heard of SAW devices? It's actually pretty cool, and it's something that you can propagate an acoustic wave across the surface of the substrate, and the metallization, it's usually an interdigitated structure of fingers, like there'd be fingers at one side and then fingers at another side, and interdigitated means that the receive end and the transmit end through the filter, they'd be interdigitated like this. And the geometries of those allow you to design a bandpass filter shape, just like you can with transmission lines in microstrip and strip line and so on. So this technology got perfected, and 70 megahertz center frequencies was, like a really good IF center frequency for making a very sharp cutoff bandpass filter. And they became popular in cell phones. I think they're still used in cell phones for the different cellular bands as part of the operation of handsets and things. So SAW filters became pretty popular. Anything that's going to be mass-produced gets perfected to a high degree. We all know that. So at any rate, we have a nice filter at 70 megahertz, and then we have a wideband A to D, one that can accept a signal at around 70 megahertz back in the day. I mean, again, with the RF SOC, 5 gigasamples per second, it's like 70 megahertz is nothing. But through time, things have changed. So 70 megahertz, the wideband A to D can respond to a signal at 70 megahertz, but what's going to happen is we're not going to be sampling with this A to D at the Nyquist rate. We're not going to have to sample at, say, greater than 2 times center 70 megahertz. We're going to undersample. And that's where this math comes in here. It's going to be an FS over 4 type undersampling, and I'm going to explain that with some math here in the next page. And then there's going to be a digital low-pass filter on the in-phase and quadrature. That's what this is, in-phase and quadrature, sine and cosine to make an e to the j with a minus sign. So this is implementing something like that, but it's actually not FIF, it's F undersample. But it's going to come down to wanting to do it in such a way that we're doing FS over 4. The verbiage in here is kind of what I've been rambling on, so I don't really need to talk through that. So looking at it in the frequency domain, we see our signal up there at FIF, and then what we want to do is we want to bring that signal down to close to baseband with an undersampling technique. Remember my simulation in my, let's see, what was the name of that? what's the name of that software, Zojo app. Remember where I had the spectrum in the bandpass signal, and we could see what was going on with that. We're going to do exactly that. We're going to undersample. So we're purposefully going to produce images of this guy that are going to line the axes here. And the objective is to get FIF to move over to FS over 4. And we're going to effectively rely on a harmonic of FS, say M times FS, which is going to make itself within FS over 4 of FIF. And that's this blue boxed equation. We want to make the absolute value of FIF minus some M times FS equal to FS over 4, with a constraint that the bandwidth of our signal has to be less than FS over 2. And that's the bandpass sampling theorem, and how to select the value of M and FIF for a given FS. The FS is actually going to be driven by this constraint here. We're going to need to make FS over 2 greater than the bandwidth of our signal. So this is the picture of what's happening. We're going to move a copy of the signal down here. We're going to fill in with all these spectral images because we're undersampling. But by landing it at FS over 4 for the center of this spectrum, we now are within easy reach of getting down to the true baseband with one more conversion. And the beauty of all of this is that the FS over 4 is not a full sine and cosine lookup. It's a very simple operation, and that's in this page here. If I want to use a frequency translation of FS over 4, and T is the sampling period, I work through the math on this, and reduces down to cosine of pi n over 2 plus or minus j sine pi n over 2. So the string of signal samples that have to come into that multiplier to downconvert it in the eye of sampling is just very simple values to implement in FPGA or some other firmware, 0, 1, or minus 1. Is that beautiful or what? I mean, you don't have to have any even finite precision integers like int16 or something. You can do it just with 2 bits, I guess. Or not even officially, it can be done in register math, I think, is probably a better way of saying it. If it was in an FPGA or even in a microcontroller. So once we have it down to centered on FS over 4, then what the block diagram says is happening here. We're going to apply a bandpass filter at B over 2, and then we're going to downsample one more time by a factor of 2, and then that will produce an image that's at baseband, and we're good to go at that point. So we've got our signal back. So I went through an example here with numbers where I was saying at the time IS-95 was the second generation cellular for code division multiple access. The block E band in the PCS band is what Quest owned in Colorado Springs, and somebody owns that band to this day, but I'm not sure. They're not doing CDMA on it anymore. But at any rate, there's the frequency, 1885 to 1890 megahertz. The center frequency is 1887.5 megahertz. The bandwidth of the CDMA signal is about 1.25 megahertz. It has a chip rate of 1.2888 megachips per second. If we choose FS to be this value here in megasamples per second, and that corresponds to 6 samples per chip for a waveform fidelity, then FS over 4 can be this value here, and then the analog IF frequency can be some M times this FS value, and it it works out in this example that if M is 9, then FIF will be 68 megahertz. So what does that mean? If the signal was exactly at 1900 or whatever I said it was over here, 1887.5, it just says that in order to make the IF work with an IF center frequency, which would be the design of the SAW filter, centered at 68.1984 megahertz, then the local oscillator could run above or below that by quarter this sampling rate. I picked, I guess I picked the low side, so 1819.3016 for the local oscillator to bring it down to the IF at 68, and then I undersample it with a 7.3728, and that signal comes out as my picture shows here. This guy, and then this is its image. What do you think? Does this seem pretty intense, or just, you know, for one thing, you should say, oh, the spectrum is very important. It pretty much tells me what's going on. If I can't visualize it in the spectrum, I'm not going to go anywhere. So that's definitely true. And a project that I worked on for a company building an ORAN, Open Radio Access Network standard base station, they were using the RF SOC. We were sampling at 5 gigasamples per second, and we had to capture as much of this ORAN band as possible for the purposes of this product development. And somebody was working on the microwave filter that was going to capture the RF. I don't remember the numbers, but I guess I'm not supposed to remember the numbers anymore. At any rate, my job was to look at how to undersample and then understand the spectrum, kind of like this upper picture here, where I would have this, and it would be shaped by an IF filter, not the SAW filter, but some other, is a microwave IF filter that a graduate student I had at the time was working with another developer on. So I got the frequency response to the filter, and I incorporated that into a model, and I did the frequency translating and the modeling kind of like this, where I could say, okay, this is what I want, it's right down here. But if there were adjacent signals and the RF filter was really right up in here, what would leak in and what would pollute the spectrum in that area? So that was kind of my big investigation, and I created a nice visual of that using something very similar to this. And that then allowed the design to move forward. Actually, what it allowed things to happen was what would be my oversampling or my undersampling factor, M, what band was that going to be, number going to be? I think it was something like 2 in this case. It was a small integer. And then also, what were the requirements to keep out-of-band signals suppressed with the limitations of the filter not rejecting everything. And then that pushed things back to the filter designer to say, make it better. And that was a microwave filter design. So it was fun. So moving forward in multi-rate signal processing, and let me just suspend for a second and go look at this. My system read when I came in here, so I don't even know if these links came in. They did. Okay. So I went to the Analog Devices website just to see where they at in software-defined radio, and they have a lot of different places to get started in reading documents. So I think I might have picked this one. Let's just see what's sitting over here. So this pretty much does everything. There's a development board example right here that can be paired up with an FPGA board. But if you zoom in on the inside of this, which I guess I can do there. Oops, my wonderful mouse. I'll try not to use that pointer. I'll just try to walk over here. These are all the analog inputs. So this one can handle some beamforming, and so you can have multiple channels coming in. And then you've got this lower half is the transmit side, the upper half is the receive side. So let's just focus on what we were just talking about with the receiver. There is IF sampling can happen in here effectively because there's two mixers. So there's two signal paths, or I'm not really sure of the details because that's somewhere up the page here, but you get multiple channels you can switch in and out, or you can run in parallel. I don't know the intimate details, but the company I worked at before, when I first left the university, was using analog devices parts for its front end, software-defined radio stuff, with its FPGA, on FPGA board. So this is the kind of stuff you get into. This is the symbol for a bandpass filter. So I'm not sure whether that's on chip, whether that's SAW, or what it is, but it's a bandpass filter, and then all the sampling stuff that goes on with that. So what about, I did a search under AMD, RF SOC, and Xilinx. So the big thing for Xilinx, and this is what I worked with in the last company I was at, the ultra-scale processors, and then you put that up with the RF SOC together, and so you get this. This is their pitch. Only single-chip adaptable radio platform. Where I'm working right now, they use these somewhere in the company. And when you watch this video or read about it, you see their terminology is DFE. And how many different, I had to remember, what do they mean by DFE? Digital front end is what they're meaning it to be. But this is just cute that I looked this up. This was where we different uses for DFE. Decision feedback, they're along with conformity. I've never done quick DFE and bumped into this, and I thought it was cute. So look up any of your favorite acronyms and see how they've been reused over and over again. So any questions or comments on that? The way I get involved with any of these products is I'm a systems modeling person, so somebody will say, we're using this part, and sometimes I have to look at some of the specifics of what that part brings to the table from my modeling standpoint. And generally, the hardware implementation engineers are really tuned into what it can do, but it's how to mold that to do the system implementation that is desired. So I get, somebody like me, or if you, with this background, you get involved with it, making interpretations on what it can do, and then I would say to the implementer, okay, how do we get access to that? How do we get to those registers? And so on and so forth. So it's pretty cool. Okay. So now we want to move forward briefly on is how to combine, sort of put together systems of upsampling and downsampling and introduce the idea of polyphase decomposition. This was problem number 3 on the project, but I'm moving it into this numerically controlled oscillator accumulator example, like I said, because I realized that what I wanted to do in pure Python really I wasn't really happy with what it was going to bring to the table. They have a polyphase filter, but it's a non-causal algorithm, and I just didn't want to take us there, because I thought if you start using that block, you're going to get blasted for using something that's not causal, in a model. I'd rather not go down that path and then have you get familiar with something that could be like a bad habit to play with. But one of the things that comes along with multi-rate sampling is, and we're already off the homework. This is something that the homework doesn't even go into. It's in the book, but I didn't give any homework problems on this, is the downsampling identity. It's also sometimes called one of the noble identities. So there's two noble identities, one for downsampling and one for upsampling. And this motivates the polyphase idea, which is very widespread in software-defined radio implementations. It might be that if you buy the RF SOC or the analog devices equivalent, it's inside the chip. You don't even know about it. You just know that it'll say it's a polyphase something, and you just know that they did that to be efficient. But to understand a little bit about what polyphase means and why it's so important, we're going to look at it briefly here. First the downsample and then the upsample. So what we've been seeing so far is this lower block diagram. This is what we've seen when we want to downsample by M. We have to put the filter out in front, and this would normally be a low-pass filter at pi over M. Remember, pi over M is the radians per sample cutoff frequency to prevent aliasing over that band. What the identity says here is that we can, with a suitable type of filter design, we can actually do the downsampling first and then the filtering. So the math behind this is is explained down below, and I'm not sure I'm going to go through it in intimate detail, but I'm just trying to motivate what is the primary idea of this identity is that here you do a lot of operations to filter a signal, low-pass filter, but then what are you going to do here? You're only going to keep every M sample. So what did this filter do? It produced every sample. What a waste that is, right? But it's got memory in it, and it's just the way it's designed. So this idea here says, oh, we can interchange the order, and what we're doing is the filter has that power of M in it. So that's just how it gets remapped. But here we can get by with a downsampling, and now we can just filter at the lower rate. And that's going to be more efficient, right? Because the clock on that is F clock over M, let's say. Let's say F clock is the rate at the lower one, and if we can drop the clock down, then we can operate more efficiently. So I think maybe I'm just going to leave it at that. The math of going through this is just plugging things in. Probably the biggest thing that I want to emphasize is what does that e to the j omega m do in the frequency response, and then how does it limit the type of filter that you can build. So I'll kind of focus on that. The upsampling identity is the exact same thing, only running in the opposite direction. So this is what we have right now. We upsample, we increase the sampling rate by a factor of L, and then filter. And that means that filter is filtering on every sample that comes in at the higher rate, even though with the upsampler we know we're stuffing in zero, so we're not, we're being wasteful there, and the filter is running at the higher rate. So you can interchange the order again by having the filtering done first, then upsampling. So this explains how this can function then, how in both cases it's going to be useful to think about how we're preparing to implement the top both here and over here. So the standard example, the one that I understand best, is when you use an FIR filter. So you just think of having an impulse response, and you have to break the impulse response up into M subsequences. So, and this is what that project problem would have done, and it works. You would write code for it, and it works fine. But I'm deciding to do something different, since I'm different than I was 2 years ago. I mean, my thinking has been more on other things. I've implemented these things and played with them a lot, but I'd just rather expose you to something different. But the idea of polyphase decomposition, just for m is equal to 2, this picture right here is nice and clear. It says, okay, all the even samples are going to go into well, the even and odd samples. So H0 is going to take the even samples and have 0 stuffed in between, and H odd is going to take all the odd samples and have 0 stuffed in between. In actuality, then you can collapse that down, effectively decimate it. So my downsampling function actually can do this perfectly because it has a phasing function in there, if you remember. It will take every M sample, but you can decide, am I going to start by keeping the first, or am I going to start by taking the second? So you can just use that third argument to create the downsampled versions of these two waveforms, just changing one parameter. So that says the polyphase decomposition is pretty straightforward. And now that they're compressed down, they're just at the integers, no 0 stuffed in between, and that's, in the book's notation, it's called E0 and E1. So E0 is the even and E1 is the odd from the original filter. Then if you were to make a block diagram out of that, what you're doing is this is just showing how you would decompose in a block diagram, and this is a silly block diagram because it doesn't do anything, and it doesn't do anything practical either, because on this side you're putting in positive powers of Z, which is anti-causal, but it's just sort of to show how you could take an H of n, spread it into its components by downsampling, and then re-upsampling and putting it back together again. So, but it's the setup for what comes next. So fundamentally, what you're going to do then is you're going to take your signal and you're going to filter it with this polyphase filter, and by putting the Z to the power of M in there, what you're doing is you're saying that's the Z transform of each polyphase filter, but upsampled by M. So the zeros are stuffed back in there. And so this runs perfectly from the input to the output with that filter. So this is just showing you, again, the concept. It's not really implementing what we want to implement, but it's just showing you how, and notationally, what a Z to the M is going to do. It's going to have 0 stuffed in between, and you could synthesize then by filtering it with one filter and all the other filters and then recombining it. So this is our starting point, the decimation system, and this is how we're going to, this is the original identity before you transform it. So if you notice what's going on here, H of Z gets broken apart to this block diagram that I had the page before with this power of M in here, and then you get to downsample after that. So this is still the inefficient. We're filtering, downsampling, but these are the different polyphase filters that were created from the original filter. But now you can apply the downsampling identity onto each one of these branches, and we have this. We interchange decimation and the polyphase subfilter, and it comes together. I realize it's a little bit hand wavy, but do you see the progression there? First it was filter, decimate, but then it was doing it on the sub polyphase strands or whatever of the filter, and then it was interchanging the order, and then the phasing of those components is all set up in here, and those are Z to the -1, so that's causal. It just says we're going to stagger everything, one sample and filter, and we're going to downsample it. So the downsample is going to get rid of the samples at the input here that don't go with these coefficients. Is that making sense? So it's really just fitting the right samples together and distributing them across those guys. What matters, though, is what does this polyphase gain you, because what we're getting here is this is a reduced length filter. The number of taps in it is approximately 1 over m times the original filter. And each of these then does multiply and adds, which is, or the sum of products, but it's only operating on a rate of 1 over m of the input. So we have a shorter length filter, so we have less math to do inside of here. We have less samples to process because we're decimating right from the get-go, but we're phasing those samples through this mechanism here. So this is kind of the summary. The number of multiplications is 1 over m times what we would have had without the decimation, and then the number of coefficients is n over m because we've broken it into pieces. And the number of additions is a very similar number, it's just 1 less. But then, of course, we have to do that for each output sample. So when you put that together, put that into a table, this is kind of the punchline part. Direct implementation, n multiplications per output sample, n minus 1 additions with the polyphase. These are the numbers that you get for the additions and for the multiplication. Most people just focus on this, say it's just going to be n over m, and the savings in multiplications is about 50. If we had a length 50 tap filter and we were decimating by 4, we'd save multiplications by a factor of about 50, which is pretty impressive. In additions, a very similar number, just not as much savings. Well, let's see. I guess the factor is 4, and here the factor is 3. Upsampling kind of works the same way, stage by stage, and finally comes down to using that identity, which is done right here, where you filter first, then you upsample, and the numbers work out pretty similarly in terms of the savings, about a factor of 4 for this example of upsampling by 4 and having a length 50 tap filter. So there's more to this, and I'm going to show you something that's out of my notes. You can see, though, where we're going to transition at this point, probability, random variables, and random processes. So there's no homework problems on that right now, but I do want to go see if I can dig something out of here that I forgot to get loaded in here. And I'm guilty of not looking for this. Yeah, there it is. I haven't had this opened up for a while. This is from a magazine that was around for a period of time and then went out of existence. It was called CSD, another 3-letter acronym, Communication System Design Magazine. So it had pictures like this in it. This is just a review, but I think it's good to go through it. This is a review of what decimation or what decimation and interpolation are. So this first picture, I took some of the figures from the magazine and just used them here. So this is interpolation, just showing you that samples come in at some original rate. You upsample by stuffing. We were stuffing L minus 1, so this is upsampling by 5. And then you fill those samples in with the interpolation filter. And in the frequency domain, the spectrum starts out there. It was a 2 megahertz spectrum. When we stuff the zeros in, we get images stacked up in here, but then the interpolation filter removes the images, and we've got what we started with. And the idea of upsampling is not because we want to be massively oversampling to send bits over a channel, but we want to be able to have the waveform ready for going onto a carrier and typically you will take it up to a higher rate to get ready to move it onto the carrier. So there you have that. In this case, it was a factor of 5, so the Nyquist frequency is 10 megahertz if this was L is equal to 5. Downsampling would be the operation at the receiver or at the tail end of some system. So you come along with a signal, and then you filter the signal, and it's not really obvious, but the idea is that this has gotten smoother because we've had to remove the high-frequency component. So that's why this just looks less jagged. So then we downsample the signal. We have, in this case, 100 nanoseconds was our period, and now we're 500 nanoseconds. So we downsampled by m is equal to 5. So the spectrum starts out looking like this. We have to cut it off over in here because we're going to downsample it, but we're saying that that's not information we're interested in. We just have to get rid of it so it doesn't fold into our spectrum band of interest. And now we can go ahead and downsample it, and we're good to go. Good review of the underlying principles. So now we're going to look at two things. I had forgotten that this was in here, but this is actually a really good thing to go through because it's kind of like, I know the math can be daunting, but I also want you to leave here with concepts of understanding the high-level principles about why we do things. And if you get so inclined when you're in a meeting and say, I know I can do that, I haven't studied it and carried it all the way through, but I know the underlying concept of it, that's your first step to being able to say, okay, now I'm going to be able to do something with that, and I'll be able to tell you more at the next meeting. You know, what I'm talking about is when you're in a meeting, people have to be agreeable, and in capstone design, I know you have to be agreeable to this, taking what is commonly known as an action item. You know, a bunch of ideas are thrown out there. People have to raise their hand and say, I'm going to take that one. I'm going to take action on that one. Somebody else takes another one. So what would life be without action items? You would be bored, and they wouldn't want to pay you because you weren't doing anything. So you want to go and study something and learn more about something with knowing some preliminary knowledge. So here is another, we're going to end in polyphase, but this is just showing you how we can divide and conquer by stages of upsampling or stages of downsampling. So here, in this article, they point out, suppose we needed to upsample by 12. We need this interpolation filter. We're not thinking about polyphase. We're just thinking about conventional upsampling. But is it good to upsample in one swoop by 12? It sounds like there'd be a lot of work involved there. And we can take 12 and write it as a product of 3 integers. We can do a 2, and a 3, and that makes 12. What advantage does that get us? Well, here they're saying we're going to upsample by a factor of 12. Our filter has to have a rejection of 60 dB in its stop band. This is just the cutoff frequency and the transition bandwidth, passband ripple of 0.1 dB. So in order to get that filter, which is this upsampling low-pass filter, we're going to have to take and develop a 388 tap filter. That's huge. Input data rate will be 1 megasample per second. We're going to be outputting at 12 megasamples per second. So with that filter, we're going to have to be pumping out computations in that filter at 4,565 mega instructions per second. It's like going to the gym and lifting weights, a lot of them. Does that hit you like a ton of weights? Like, that's a lot of lifting, a lot of cycles in our processor. So now they go down here and they say, okay, let's upsample by 2, come up with that filter design. It's much more doable, 121 taps. Upsample by 2 again, redesign it another 17 taps in this case, according to their design rules, and then take it up by 3, and works out to being 13 taps, I'm not going into the details of that, but I'm just trusting them that they did this reasonably well. So now the required computation rate scales upward depending upon what rate you've increased by. So here it's moderate, heavier, and then heavier still when you get to the end. And these are the individual processing loads in each of those stages. But still, when you get to the end, the point is that that and that are significantly different, a factor of 4. Impressive, right? I'm impressed by it. I mean, I didn't grow up being a multi-rate processing person, but I became that because every system I work on has to do it. You could do the same for the downsampler, similar type argument. So I find this example to be pretty powerful. It says don't do it all at once. That's trying to do too much. And, you know, I'm guilty of that over and over again in my life, not in engineering, but in activities. I like to just go, 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 and not take a break. And guess what? Your body doesn't like to go, 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 go all the time. So that's how my gluteal tendon got so messed up. It's hard to explain exactly why it got so bad, but it got a little bit bad. And I thought, it's going to get better. I'll just take it easy a little bit, probably not nearly enough. It got worse and worse, and pretty soon in August, just before classes started, I was in bad shape. Try to get your body to heal. I'm doing that now, and it's actually working really well. It's definitely not back there, but look at your life sometime. Probably not right now, but in the future, you might make the same fatal mistake that I've made. And I've done this in different areas from over-exercising. But as an engineer, there's some application in there. Don't try to do too much all at once, or try to do it all by yourself. So here's the example rerun again with the polyphase. So here, the original filter length was 388 taps to go from upsample by 12. So if you take that length and break it up into 12 polyphase filters, remember how we were sampling the filter out into polyphases? That's 12, because you're going to take and divide 388 by 12, and you're going to have, by 12, and you'll get 33 taps per polyphase filter. So the computation rate now is only 396 MIPS in these polyphase filters, and then you'll be strobing across there and sampling those outputs. So what it would look like for upsampling and downsampling with the polyphase would be the upsampler would be breaking it into the subfilters and then sampling the individual outputs. The rates here are reduced. This diagram doesn't show that, but we had a phase decimation going on to feed this at the lower rate, feed each of these at the lower rate, and we weren't cheating, right? You can hopefully, if you want me to, I'll push this on Slack so you can have it if it'll be helpful in your future to say, let me review what was going on here. But this input is going to get upsampled, but we're doing it, never mind, I was thinking of decimation. In the upsampling, all the samples flow in here, but at the lower rate because we haven't upsampled, and then we collect them out here at the different phases. And this thing is collecting at the high rate. You know, for every circle around here with the switch, that's at the L times F clock in. But these have been done at an increased efficiency because of their shorter length filters. Is that good? And then on the other side, there is the decimation going on at the input. That's what I was thinking was missing. So these filters are driven at the lower rate, and then they combine at the lower rate because you're decimating how you feed in. This takes phase 0, this takes phase 1, phase 2, and so on down the line. So that's the polyphase idea. I think polyphase is probably the most popular method that people use today. So good. Are DSP people thinkers, or are they just doers only? They're thinkers, right? I think engineers are thinkers in general, because we can't be competitive unless we can think. We can't field a product. I mean, unless you want to be like some countries which want to just steal ideas and then manufacture it. You got to be authentic and come up with your innovations that are going to truly make the difference. So we're going to take the break now because it is that time. And I'll be interested now that I'm not fainting today, we're not doing an exam, is this projector going to stay going? Because I told you this last time, didn't I, how they made the changes? In case you don't remember, I'm going to pause so I don't have to put this on the video. Okay, the video just came back on, so I was segueing by looking at types over here, which I'm not going to go back to, but I was talking about how we want to get going on Project 1. And just backpedal slightly. In Project, there's comments in the Chapter 4 material on sampling theory. There's a section down here. We finished in the notes before break at multi-rate sampling and polyphase sampling, and that brings us just above probability random variables and random processes. So this was a time to segue into working on the project, which is a parallel activity with homeworks which will be less demanding. So we were sitting over here looking at Project 1. I've been editing it. I haven't finished editing it. My biggest objective is Problem 3, and I've got that underway. But what I was saying is that this should be a fun project. It's going to be work, but it's not going to be hard math work. It's going to be coding and interpreting your results from your pictures, your plots, and whatever. And that's what I spend almost my entire day doing all the time. I mean, I can think about the hard math stuff, and I scribble that out, and I write it in as notes in my Jupyter notebook, so I know what I did. I don't have to explain that to the people I work with. They want to see the higher level stuff, right? But I send my immediate boss, who's a very tech-savvy person, a document I produced yesterday on types. I sent my coworker, who's the FPGA implementer alongside me, I sent him a document that described a digital filter design required for the transmitter of this project, and it goes through all the steps and the details, and I modeled everything in lots of detail. He can get access to my code on Bitbucket, which is similar to GitLab and GitHub. They all use Git as the repository management. He can always go grab my notebooks and my source modules there, but still, in the end, I think a lot of us communicate with something like this. What do you think? Maybe you don't see it in paper, but you read something on the internet or hear a talk on the internet. So I think for our entire lives as engineers, we are going to be communicating with some words on the page and pictures on the page. I'm okay with it. It is what it is, and I think it has to be that way. That's how you engage people, and on teams in particular. I did some cool demos for my team with animations in Python with sliders and things, because I was told by my manager they don't know something, and I tried to make it as clear as possible. I put on all my teaching hat paraphernalia and was all geared up to try to blow them away with, I want you to understand this. I want you to see some pictures, not worry about the math initially. So I got a lot of compliments, so I feel like I must have done something right. They're still counting on me to figure out the details, and they're going to sit, at their respective high level and just hope that it all comes together. So this project is the idea of getting introduced to Jupyter Lab, which you've already been working at. You will be using PyAudio Helper in the last half of the project, and you'll be using the IPython widgets to make GUIs in Jupyter Lab to drive your PyAudio Helper real-time app. And actually above that, well, not above that, below that, besides the sample notebooks and everything, We are using what's called the SciPy stack, and I've talked about that before. PyLab is not something you can run officially anymore, but I still like to use it. I use the equivalent of it. With Python 3.9, you can run PyLab. I've been doing it, right? You've seen me do it. It'll just give you a deprecation warning. But I have the notebooks figured out over here without it. So I can make that clear. So rather than running PyLab, I run those 3 lines instead, and I get the same impact as running PyLab. Most professional developers would not do this import of everything, and I have to convert my code when I write it to go into a module. I have to import NumPy as NP. That's the standard terminology that people use in the industry, so I convert it usually later because I use VS Code to help me spot all those places where I need to add NP dots. I was doing that just yesterday, as a matter of fact, or other NP dots spread around and signal dots and things like that. But at any rate, so I don't want you to take on the full challenge, but I want you to take on a lot of the challenge just to get up and running. So back over to here. First problem is writing your own version of LCCDEs with non-zero initial conditions. This one exists in Python. We looked at it, but I don't know how it works myself. I haven't studied their code. I want you to just take my template code and figure out how to write your own. I think it's a really good exercise to learn how to code in Python and do something that I've commanded you to do, because that's kind of what it comes down to in reality. Whether I command you doesn't matter. I'm always commanding myself. I guess I'm going to do this because I need to show something to somebody. And that's, what's that called? Self-analysis or self-direction or something. I mean, that's another trait of an engineer, though, is being a self-starter. So I will say that. Multi-rate sampling theory, you're going to put that into action and pretty much figure it out in both time and frequency. And then the new problem is the DSP component, the phase accumulator, and then making it into an NCO, numerically controlled oscillator, which is the digital equivalent of a voltage controlled oscillator, or VCO. And then a simple little exercise involving an IIR notch filter, but that comes back again in the last bullet when you're going to use PyAudio Helper and go through 3 individual tasks. A linear chirp generator, which is going to be fun, but you might want to use your headphones because you're going to make some really kind of wacky sounding things with chirps, and you're going to get to using Python objects in there. And then speech with noise, that's an experiment where you're going to corrupt a signal with noise, and you're going to try to design on the fly with GUI sliders the cutoff frequency of the filter in such a way that it's the most intelligible to you. It's very subjective, but you're going to be trying to discern this speech pattern and with a lot of noise, and you're going to want to just figure out, do I want to band limit it more to make it more intelligible? I mean, it's going to be a bandpass. I think it's a bandpass filter. Actually, I have a bandpass example, but you're going to be just playing around with intelligibility. So it's kind of a human hearing characteristic, but you're going to be applying an on-the-fly DSP so you can listen to it. And then the last one is jamming mitigation with a programmable notch filter, actually 2 programmable notch filters, and that will use the same notch that's studied up here, but you're going to be implementing it right out of the book. I have it in the SIGSYS module has a notch filter defined in it, exactly the one needed, and you'll use that in real time though. So the 5th bullet there is the most thrilling because it's all real-time DSP. It's all running in real time. So the first problem seems very simple, and it says I want you to come up with a difference equation solver with non-zero initial conditions. So in reality, all you're trying to do, and I say in reality kind of subtly, All you want to do is implement that in code. I will give you a set of coefficients, and then I will give you the initial conditions. Oops, got to turn that off. Haven't used this since the first week, so I have to remember how to use this again. So I give you a sample in the notebook, and what you have to be able to take on is initial conditions, initial values on the output, and initial values on the input prior to n is equal to 0 will be stored in there. And this is pretty much identical to what is supplied by Python. I've honestly never actually tried to do this problem using that tool because I just took this on as this is a good exercise to try to learn about writing some code. So the examples that you have to do are actually written down right here. These are the examples that you're going to run. You're going to do this, and then you're going to do the second one. So you're going to put in some initial conditions, and you're going to get the output. So I pretty much hold you the hand. You're going to take the input coefficients, convert them to an array of coefficients, so you can use vector operations inside NumPy. You're going to create a zeros array, so you have a place to put your output. And you're also going to create a state vector, which is going to be a place to keep your states for your filter when you're doing your sum of products. And what do I mean by states? I just mean that when you have to carry out each of these sums, what are you going to do? You're going to take a new value from the input, and then you're going to load in, you're going to have loaded the past values, and you're going to run this sum over the coefficients times what the state is of the filter, the newest value and then the oldest values from the previous iteration, and that holds true for both the input and the output. Once you start coding this, you'll see how it sets out. It sets out very nicely, actually. But so the state is just an array that holds the past values of the input, and the way I use the state is when I first get a new sample, I will update that state. So when you're writing your code, your state initially is going to be all zeros, and the first sample that you process, you will put in here, and then past values of the input will be put in here according to the initial conditions, and zeros otherwise. And likewise for the output, the first output value, or the last output value, is the first element of the state. The present output value is the output, so the state doesn't hold that value. It could, but it's not needed to calculate the difference equation, because the difference equation takes the sum of products times the coefficients b times each of these values, coefficients a times each of these values, adds them all up, and that's the output. So that's the type of thing you do in your code. Some helpful hints are in here. So let's go look at what I have in that notebook. So when you're in that notebook, you've got this framework and the examples. And then here is what I give you to get started. So I'm giving you a framework. I'm pointing you in a certain direction. So some of you may want to take your own total tact on it. I prefer that you follow my hinting so that I can understand what's going on. You are going to get an output. You won't know if the output's right or wrong unless you were to take the time to go run it through Python's L filter with initial conditions. Like I said, I've never tested it before. I think I did my solutions in a different language. I used Mathematica for one of them, because it has the ability to do initial conditions analytically. At any rate, you can see that I've got arrays or I have conditions that are running. Fundamentally, though, I have a for loop that's going to run over all the input samples, and I'm going to use a feature of Python called the function enumerate, which returns both an index and the current value at that index. So it makes writing a for loop pretty handy. I get two things back right away. How many of you have used enumerate before? Okay, you know the value of it then. When did you first learn about enumerate?
I had to do a lot of data analytics on current sensor where I took all of the raw data.
Okay. Did you look at a tutorial ever anywhere and see somebody said enumerate, you should learn how to use it?
I got some legacy code and saw someone using it.
Okay. You got something, though, where you saw people were using it.
Yeah.
Because when I first got exposed to Python, I just thought, I'm going to have a loop, and I'm going to be all on my own to figure everything else out. But then somebody said, you should consider using enumerate because it gives you two pieces of information, and it just makes it a little bit nicer to write a loop. So your code goes in there. I have the state initialization code up in here. You'll have to maintain your state. But what I recommend doing, and this is in Jupyter Lab, I didn't write any of this out, but you have access to a pretty nice function that I believe I would recommend using. I thought I had some answers in here, but consider a NumPy function called roll. What you want to be able to do is every time you take in a new sample, you want to take your state vector and you want to roll it to the right to make the values the old values. The value at the end with the roll function is going to come around to the beginning. Now, is that going to destroy your life? If you write the next line of code after you do a roll to the right, you write over the first element of that array with your new sample, now you're good to go. Can you visualize that? What I do in Python all the time, though, is I will write a little example. I go in the Jupyter Notebook and I say, I do this constantly. I'll say x equals, I can't type fast enough on this keyboard and my mouse is jumping me around. So if I do that, I'm not good to go because I'm only creating a Python list. I have to wrap that with array so it becomes an ND array. Let's just prove that by, there it is, it's an array. So now what happens when I roll on that array, I'm just using control / to comment and uncomment. Put y down here. I'll put x in here, and then, what was the syntax? Shift-tab. I'm back to the second argument is the only one I really care about. Usually there's some examples down here that may be useful to you. Like there's a nice example. Roll right by 2, roll left by 2. So get used to using that too. You're not high and dry. The Jupyter Lab has nice features for getting syntax help. And of course VS Code does too. So let's roll by 1. That's what you're going to be needing to do is roll by 1. And there it is. 1, 2, 3 is now shifted to the right by 1, and I just zapped over that. But suppose the next input was, what I can do here is I can just say y at 1 after my roll, I want to be equal to 10. Well, y at 0, sorry, 0 based. I'm thinking Julia. Okay, so see, now I'm good to go. Now I can use that in a sum of products in my code up here to form the output that I'm caring about, and that output is, it's back over here. Your sum of products is, say, for the input with the BKs and these guys, and then the AKs are over here too. And as long as you load up your state vector with your initial conditions, this thing is all ready to roll down the path. One sample after another, and the outputs will come out. Because you will have filled, you will have propagated, you will have initialized, this state vector, so it has your initial conditions already in it. So the very first iteration of the for loop down here is going to be just using state as it exists already, except you're going to first load it with a new value. The state is filled, but it's not filled with the new value of the input. So according to the code over here, these values are filled in. You have to put in your new value, and then you roll, and you can just let the roll sit there until you come around again, and then you can fill it in when you need it, the first front-end value. You can play around with different ideas. I'm not asking you to time your code to be the fastest thing. I just want it to work, period. So am I giving you some motivation to get started? And if you haven't done this, you got to do it. So once you start writing a function, the other thing is you can use the debugger. If that is helpful to you, sometimes the debugger is annoying and it doesn't always work the way you'd like it to. I'll just show you, I guess I should show you a quick example. I'm just going to do this to show you the advantage of using the debugging of a function. Then I would replace this probably by print y, or do a formatted print, however you want to do it, but I'll save that. And then I'm going to put a line below here to call that function. And I should be able to, I didn't compile this yet, did I? And this should have been done. Okay, now it's built. So now I can run tab, and I've got help to know where my function is. So there's my function, and what I'm going to do is I'm going to turn on the debugger, go from simple to more complex, and then I'm going to go up here and enable the debugger. I'm going to get rid of that window so I have more space. And then I might set a breakpoint right there, and I'm going to do my Shift-Enter on that cell. And there I am. I'm at the entry point to this cell. And now I want to look at variables. And you see a lot of variables. It's very cluttered up because I'm in the entire workspace of Python. But because I'm wrapped inside a function, what I'm going to do here, which button do I want to pick? Do I want to step over? No. I want to step in, right? So I go over here, I go step in, and there I am. I'm called my role. I'm in the first line. And if I look for variables, there are none. It's all of a sudden a clean slate, and now I can see clearly what's going on. So now I'm going to go over to here, and I'm going to step. So it's not perfect with ND arrays because to get inside of it still takes a little bit of effort. If it was scalars, I'd be able to see them very easily. But I can step along, and if I was in VS Code, I get some better features. I can go to the debug window, and I can type commands, and I can hover and things like that. But still, this isn't bad. You could add some things in here that would allow this to break apart more, to see exactly what's inside of there. I don't particularly like this feature as well as I do with VS Code. It's kind of pedantic. I mean, look how detailed it is. It's telling me index 0 is, well, let's go to X. I just know that each index holds an int32, but I don't know exactly what those values are, and sometimes that's what I'm more interested in. So VS Code's debugger is a little bit nicer. But it is an alternative, and there I just hit the run button and I'm done. I can close this out, take that back. So that gives you some idea there. This is the help window, though, where I can interrogate things. So I guess, does that pop up right away? when I hit it. It popped up at the end, I think. Should I do that again, or do you want to figure it out yourself? I'm just gonna move on, I think. I've been trying to practice with this debugger myself more in my work, because I switch back to VS Code if I'm having a really tough time with something and want to see it better, and then I switch back over here because I document things better over here, and it's faster. That's the nature, though. You kind of have to work at stuff until you feel like you've tamed the beast in a way, because that's what it kind of comes down to at times, is these are my tools, are they working for me? You want to make them work better. So the next project is fairly benign looking as well. It's going to bring in a signal of 2 sinusoids, immediately downsample it, then upsample it, and then go through a low-pass reconstruction filter, and you're just going to use FIR-Win, which is part of SciPy.signal, to design a simple filter. So you follow all these steps in here, and the idea is you're going to be getting the waveform plot, you're also going to be getting the spectrum plot. So one of the important things in this exercise that you get to do in Python is do a spectrum plot. So the first thing is you're going to generate your waveform, and then I'm going to have you use a function in SIGSYS called Simple Spectrum Analyzer, using the Hanning window, or the Han window. And so there's the spectrum of the input, and that's normalized to omega over 2 pi, so we just have to say this one's at 1/20th and this one's at 1/3. So that's where these lines occur. But as soon as you downsample this with what I've specified, some aliasing is going to take place because I didn't pre-filter it. So you're going to break the rules, but I'm doing it on purpose so you can follow the spectrum along. So what the tool is to figure out what's making sense is I have you use find peaks, and you're going to be taking this spectrum in decibels like I have it here, and you're going to set a threshold on it. So here I set the threshold, find me a peak if it's above minus 15 dB. So then right here, I just have this nice little list, formatted list, so I can see, okay, I have a peak at 0.05, it's down minus 3 dB, and I have a peak at 0.17 hertz relative to 1 sample per second. That's at minus 6 dB. So I was wrong in my numbers. What was I wrong by? I guess that was right. There's a 2 up there, so it's 1/6, and it's 1/20. So, yeah, that's pretty close, right? Let's make sure we know theoretically where things should be, because I'm asking you to do that as well. So it's 1/20, and it's 1/6. I'm just using a tuple to list it off, so there it is. So this 0.17 is that. And hey, this is formatting that you've done before in C, so if you want more decimal points, you can have them. I personally like the ability sometimes to just sort of not see all that fine gritty stuff, because I know what I'm looking for theoretically, and I know I'm going to be pretty close to it, so just 2 points is probably better, so you can follow that pattern. But now you're going to decimate this, so what would happen if we did that up here? It's just going to be, according to the problem statement, you're going to downsample by 4, right? Is this making sense? So I want you to figure out theoretically what's going to happen when you downsample by 4, but let's just go in and see exactly what is going to happen when we do that. So I can hack this a little bit. or I can preserve my code. Let's just copy this cell on the clipboard, and then I'm going to insert another cell below. So right here I'm going to say in my block diagram, sorry I'm jumping around, but I'm just trying to give you methodology that'll make it easier for me to understand what's going on. What did I call that? I called it Z1. So let's just do that in code so we can track it better. We'll call that Z1 is equal to ss.downsample x by, is it 4? Okay, and then all I have to do here is say that Z1, and if you want to be, again, crazy like me, sometimes I get caught by errors in arrays not being tracking because I've made some changes somewhere, so I'm just going to make my frequency axis track with my spectrum. So I was doing this just yesterday, for example. Pluto Notebook forces you to do this. They don't give you an option, so. Okay, so did I do enough changes there? I think so. Okay. So there it is. Now, when we downsample by 4, we have a spectral line at 0.2 and one at 0.3. And what did we have before? We have the values there, but the bigger one was lower in frequency 1. So now after we downsample, the bigger one is still the lower frequency value. But something else is probably happening here. So you're going to have to explore what the downsampling is. So, you know, of course, the cool thing to do here is to just simply copy this, put it in for the new signal, and it's going to spectral analyze your peaks, and then you can start making sense. Are these numbers what I expect to be happening from the downsampling? And then you're going to repeat it to go through the next stage, which will be the upsampler, and what's that going to do? And you're going to see a lot more when you upsample. Let's just see how hairy this starts to get. So let's just do that. So Z2 is ss.upsample. What was the number again? It's 4. It was up and down by 4, wasn't it?
Yes.
Okay, so now this should be in another cell, but I'm just going to do it like this.
Line 3, do you have to change it to Z2 as well?
Yeah, yeah, right here. Yep. Why is it so slow? I don't know, except upsampling has a lot more samples per auto. There we go. Surprised? Upsampling, though, produces all those copies, right? So now what you have to visualize is that this is what we had. Crap, still goes out. Yeah. These guys aren't going to believe me.
Dr. Triboli's been having a hard time believing it.
I know. Well, but you guys are, we're all witnesses, right?
I keep telling him it controls. It does go off.
Yeah. Yeah. Okay. So what we saw before we went into the upsampler, we saw something like this, right? So now we're going to have 4 images when we go upsample by 4. So it flips like an accordion. So here, flipped, and then back again, flipped, and then back again, flipped. And this is up to the folding frequency. So in that sense, it looks totally correct, doesn't it? this axis is now different because we've upsampled. So this is what this exercise is about, trying to get your brain wrapped on that, because you know, I do things in my modeling at my job right now, and I'm doing upsampling, and I'm seeing some of this garbagey stuff that gets in there. The interpolation filter is supposed to get rid of this stuff, but you will see little tiny hairs sticking up down there, and you're going to be doing the filter after this too, and you'll see a little bit leaks through because the filter is not perfect. The decibel scale is very good about letting us see. 60 dB down is very good though, so I mean it's not going to be that annoying to you, but it's still going to be there, and you have to become tolerant of things like that and not freak out. It's like it's not perfect like the book, but it's not perfect like the book because we're doing real things. So okay, let me go back to the tour of the project. I think this again though is fun, and it's tedious, and that's something that I don't think ever in engineering anybody ever said that it wouldn't be tedious. I mean, when I first was working with somebody on FPGA code and I was system modeling, I saw what they were having to do, or actually it was embedded systems, microcontroller stuff. I said, this is so incredibly tedious, and he said, yes, but I get paid for this, so he was really excited about it. So new number 3 will be this periodic signal generator. I've already given you the code. It's eventually going to be in Scikit DSP-Com, but I don't have it in there, so I'm going to give you a code module that will house it. This is what the block diagram looks like for it. It's an accumulator that runs, I'm using 64-bit integers inside of this code right here. I'm driving it with a 64-bit integer input, but I'm making the accumulator roll over as if it were 48 bits. In FPGA, you can have whatever bit width you want, and in the DSP slice, you get a 48-bit accumulator automatically, but you can make any bit width you want. You guys are experts on HDL because you've been taught in it. I've just learned on my own and don't know it very well. But so what would I do is in Python and NumPy, we have unsigned integers that can be uint8, 16, 32, 64, 128, and so on. So I can create my own finite precision integer, and I would want to use one that's bigger so I have some overflow. So what I'm doing in this is I'm using a 64-bit unsigned integer, and then I force it to roll over with a modulo function that rolls over when it gets to 2 to the 48. Now, these are really long integers, but that's what is done in practice. You have a lot of precision in your accumulator, and you can set as an input, if you want to build an oscillator out of this, you can set this delta K as like a bias term that keeps pushing in here and makes every time this loops around, it's going to take its old value from here, it's going to add the new consonant, and what's going to be happening out over here is it's going to be a sawtooth. It's going to be climbing up. When it reaches the top of the unsigned integer, what does integer math say it does? It flips over again, right? It goes back to 0 at that point, because that's the nature of a word of binary digits. When it hits the top, it rolls over. If it was a signed integer, it would go to the 2's complement value, but I don't want that. For this problem, I want an unsigned integer. It just simply rolls up and starts over again, and that's perfect. So I want to set it to be a particular input, produce a particular ramp rate, and that's going to be relative to my clock, and then multiplied by 2 to the 48. So that tells me integer-wise what that step has to be. I haven't decided what I'm going to have you do in this problem yet, but does this sound kind of interesting, or does it sound weird? One of the things I do with this, though, that I didn't comment on, and it's done in a Python class, is I have methods like update and output a sine wave, output a square wave. But I also have another method in here called pause edge, and you guys know more about this than I do. You've seen that before, right? When you program an FPGA, where you do some code when you have a positive edge of your clock something or another. okay? But that's the way it works. I mean, I did some programming. When I first left the university, I started playing with some FPGA boards I had, and I learned a little bit, enough to be dangerous. But then I worked with code that others had developed, and I saw pause edge all over the place. So when the clock is rising up, you do something. When the clock comes along with another positive edge, you do something again, and that can produce a signal flow at the output. So I created an event that returns a Boolean value every time the accumulator rolls over, so that way I can have events occur, and that way it can produce a sequence of values that's coming out. It's like a signal generator then. Does that seem? And it'll be at a rate that's controlled by the center frequency or the sub-frequency of the clock. The clock is maybe at 120 megahertz, and I want to produce a signal that's at 5 megahertz or 5.25 or something like that, and I can get that with my accumulator. I can get a rollover that occurs at a rate that's a submultiple of the clock rate. Cool? I mean, you don't change clock frequencies that often in an FPGA, so you have to come up with means to synthesize waveforms, and that's what this can do for you. And then it also shows at the bottom here an input. So mine is a mixed data type implementation. That can be a float number. And if you're wanting to tune the NCO in a phase lock loop, like a tracking loop of some sort, which is a control system, you can bring in an error signal that comes out of a phase detector, like in an ordinary phase lock loop, or a timing error detector in a symbol tracking loop, or another type of phase error detector using a carrier locked loop for a modulated carrier, or what I'm doing with spread spectrum, a delay locked loop in spread spectrum despreading. I'm rambling off a lot of stuff, but these things show up over and over again, and I've been bumping into them so much lately that I thought it'd be something to play with. Third one is, this is actually fourth. There's a typo in here in my auto numbering. This should be number 4. It's a frequency response of a notch filter. So that one's pretty straightforward. It's actually very straightforward. Number 4 gets into a sequence of parts A, B, and C, which is using the Pi Audio Helper, which this is, for me, maximum amount of fun, because you're actually doing something in real time. It has a heartbeat to it, and it's producing something you can listen to. If you don't like audio and don't listen to music, this is probably going to be kind of mundane for you, because you're maybe up at picture level or something like that, two-dimensional. I'm fine with audio, though. I play music, so listening is a fun thing. So this will use this interface, which is built into your computers, and then the framework that I have is in the dashed line allows you to process frames of samples. And we talked about this in the demo that I did weeks and weeks ago. But the main idea is that you have a callback function that you will write, and I have templates for this that look something like this. And most of the time what you're going to be doing is you're just going to be looping a frame of data which is not coming in the input, the in data you see up at the top. Instead, it's going to be from a function or a class, a Python class I wrote called getSamples. And it's going to be maintaining a frame count, or the frame count value is how many samples normally comes in this callback from the PC's audio system, but I'm just going to create my own signal of frame count samples with this method called getSample. So that way I can just give you an audio file, music or voice, speech, whatever, that just keeps looping, and you can then play with it as if it was running in real time, and it's not streaming into your computer. Is that fair? You don't have to have a microphone. You don't have to have your own audio generator or something. I mean, people do like to play music that they would pump into their system from YouTube or one of the other audio sources on the internet. But you're going to create your own, and then it's stereo in this case, in this example, and then once that loads into here as a frame's worth of left and right, then we can bring in a value from a GUI slider that has its value held in the instance variable value. So left gain and right gain are just the IPy widgets, which get defined up here. That's how you define a widget. Once you import the widgets into the notebook, you can just, I'm creating float sliders, and you get to set the values. Have either of you done GUI programming ever? Have you ever wanted to do it? No? Why? I'm just...
It's hard. I mean, I've looked at tkinter programming for GUIs, and it's
Yeah.
complicated in Python.
Yeah, I agree. I've looked at a lot of different stuff. I've done C++ for Windows, and the Zojo that I wrote the apps I demoed in here a few weeks ago was pretty easy for me to get into, and then I wrote some object-oriented code for doing plots and things. But this is actually pretty easy. It says I import widgets, and then I have a method called float slider, which lets me instantiate what that object is going to be, and it's going to be called right gain, and it has one parameter called description. Is it going to be continuously updatable? What's the initial value? What's the min value? What's the max value? What's the step size? What's the orientation of the GUI element itself? So in terms of working with widgets, that's pretty straightforward, right? And again, this is in your notebook, and you just get to tweak it. So I think another thing I've learned about software that I've been having to do the past X number of years is people talk about patterns in software. Have you heard that term before? I think patterns is life, right? We have patterns and we see things. So I think software is just like, I see that basic form, I just copy it and I make some changes to it and I get to use it again. And we're using patterns, I think, all the time. I don't think we would do as much in life if we didn't have patterns in some sense. If everything was always totally brand new to us, never been seen before, we would be floundering a lot. I think you start learning patterns when you're a baby pretty readily, like who gets more attention, mom or dad, from the infant. If you've got kids, I would say my wife is the one that took, the mother always takes more, but in my household, because my wife and I both worked, we were both very intimate, and I was on a sabbatical, so I was feeding them all the time. Twins, one on this side and one on the other side, 2 bottles going down like that. It was fun, frustrating, but at any rate, this is code. It's very easy to maintain. It's you'll just do that to get your widgets. So once you get your widgets built, then you get these 2 buttons from, you first run it, the start stream and stop stream, and the status of it. Those buttons are part of the PyAudio helper. And then here's the 2 vertical widgets that were created in the code above. And you can see in the code right here, this line just brings in those 2 widgets. I'm just using another GUI term, which is used in tkinter, I believe, also. It's a method from the widgets library called horizontal box. And if you think about this, this is a list in Python. It just says make a list of these objects. Left gain slider, which was vertical, right there, and one right next to it is the next one. Seems pretty simple, doesn't it? And it just says put it down. After these other pieces of code I've run for the DSP IO, it says put your widgets down, and they're going to be there. And when you move the slider, you'll be running into the variable, which is up here, the value. And because I've done something that you generally don't like to do in code, and that's called use globals, but this is the only way to do it. This callback comes in with this list. We can't touch that. That's defined by the audio subsystem. So to get variables poked inside of here, we can bring them in as a global. And you just list it as a global. It actually works without that, but when I wrote this to the Scientific Python conference and presented a paper, they said, you can't do that. You have to make it a global. And I said, why? It works without it. And then maybe it doesn't work sometimes, but I've since then agreed that yes, making it a global is good. So left gain and right gainer objects are now available inside this callback, and they can run our system, and you move the slider and you're listening to it and it works in real time. If you've never done a GUI before and then a real-time audio GUI, it's like this is going to be, to me, this is what makes it so much fun. It's like I get feedback. I see something happening. So you'll do that. You do it for the chirp signal right here. And this is just with an oscilloscope connected to the output of my computer to see that I am getting, well, this is actually done inside of here. Never mind. It's done with the waveform using spectrogram. 2610 had you do this, right? Spectrograms. Same idea. And here's a GUI that you're going to create to control the things in this application that will play in the left and right channels. And this is what might drive somebody crazy, because you can make a lot of noise with this. It's going to be chirping up and down, and it's going to be kind of annoying sounding. My wife does not like it at all. You're going to do an audio application, and this is going to be an adjustable low-pass filter, and you're going to be taking a male speech vector that I have from a library that's freely available on the internet. It's recorded at 8 kilosamples per second. It's in the zip package. And then we're going to be taking some random Gaussian noise, which is why we're going to be talking about that in the lecture part. Getting the variance set right on that Gaussian noise so that it's going to be the signal to noise ratio. The speech power divided by the desired signal to noise ratio will give us the variance that we have to plug into the noise generator in the callback loop, so it's controllable with a slider too. Bring up the noise, bring down the noise, something you probably never do, but you've heard noise on a radio signal before, so that's what you'll be doing. And then you're going to try to filter it, and you're going to make the cutoff frequency of that filter be a variable that can be designed on the fly, because Python is pretty fast. In that callback function, it will redesign the filter, and then it will use it right away using L-filter and the initial conditions we talked about. Remember that demo I did where a signal streams along and you wanted to have it continue again on more data without starting over again and having a glitch in it? We'll be taking advantage of that. So that's quite a bit of fun. And there's a demo app for that that's actually in the notebook that's not here. The last one, though, is just coming up with this. I give you a male speech, and it has 2 sinusoidal tones, but it's in a file. So you get this together. You don't know where those jamming tones are at. And you're going to be implementing and listening to the signal that's been processed through 2 notch filters, and you're going to have sliders on those notch filters so that you can listen to it, and then you can adjust the center frequency of the notch until you hear the jamming go away. Now your brain is going to say, all I have to do is analyze this waveform with a spectrum analyzer, and I can see exactly where those jammers are, and that will tell you what you need to set here, but I still want you to just do it sort of on the seat of your pants. Just move them around until you can get it to go away. Does that sound cool? I mean, that's a real-world scenario where we do remove jamming, not in audio necessarily, but, you know, adaptive music and other things could do that. So that's the end of it. There's hints and other things. There's a lot of comments in here too, a lot of hints and helps and things. So I've been doing this for a long time, and it's always been fun for people to work on, not free of work. So I would get started on this and start going for it. I'm going to stop the video at this point, and I'll be up in the lab for a little while.